Welcome to the second lecture for the course Probability Methods in Civil Engineering. This is basically the starting of module 2. In this module 2, I will cover the concept of random events, which is very useful in the probability methods. In this module, there are a couple of lectures, 4 or 5 lectures will be there. In the very first lecture, I will cover the random events and probability concept. Basically, we have to know the concept of random experiment first, and before that, what is an experiment? It says a set of conditions under which behavior of some variables are observed. And when we say that a particular experiment is random, that is a random experiment, in those type of experiment where it is not possible to ascertain or control the values of certain variables and results varies from one performance to the other performance. For example, if I say that if I throw a coin and I want to see what is the outcome of the throwing of a coin, I cannot say with full certainty that what should be the outcome, whether it will be the head or it will be a tail. So this kind of example, that is tossing of a coin and similarly a rolling of a dice, where I cannot say the particular outcome from that particular experiment, then the outcome of that experiment becomes random, and this kind of experiments is known as random experiment. When we take this random experiment, there are different types of sampling techniques. One is with replacement and another one is without replacement. In the case of with replacement, each item in the sample space is replaced before the next drop. Say, for example, if I say in a box there are few balls and the balls are of different colors, and I want to take out one ball in random and I want to observe that what is its color. Now if I take out one ball and place it back to the box again and do the next trial after replacing the ball, that is known as the with replacement. If I don't go for this example and if I give the example of the tossing of a coin, this is also can be treated as with replacement sampling technique, because if in the first trial I get one head and I am going for the next trial, that means all the options, that is all the possible outcome, head and tail, both are with me. So this kind of experiment is known as the with replacement experiment. There is also possible that we can do the experiment without replacement also. In the example of drawing balls from a box, we can just take out one after another a particular color of ball and keep it outside, so that we will know later gradually in this course that these two kind of sampling technique is different when we are going for the definition of or the computation of probability for that particular experiment. There are different types of this kind of experiment. One is that independent or simple experiment, and second one is compound experiment. In this independent and the simple experiment, it says that the outcome of one experiment has no influence on any such other experiments, or also it is also not dependent on whatever the outcome in just previous trial. Say for example, if I say again that tossing of a coin, then if the outcome for a particular trial, if the outcome is head, it doesn't influence it doesn't have any influence on the outcome for the immediate next trial. So this kind of experiment is known as independent experiment. Second one is the compound experiment. It says a new experiment by performing n numbers of experiment in sequence. For example, tossing two coins one after another and getting head for both the coins. So I just want to show my experiment here is that I throw two coins and I want to see the outcome for both the coins. It comes head. If I give the example of rolling a dice where the possible outcome is 6, that means the number 1 to 6, I can say that what is the possibility that the summation of the outcome of both the dice will be greater than or less than a particular threshold value. So this kind of experiment, it says that it depends on the outcome of one particular experiment depends on the total performance, or the success rate of the experiment depends on the mutual performance of both the all the trials that we are performing. So this kind of experiment is known as compound experiment. There are different possibilities of the outcome for a particular experiment, and based on the number of possible outcome, it can be divided into two different parts. The first one is the Bernoulli's trials. It says if a simple experiment has only two outcomes. For example, as I said that in case of tossing a coin, there are only two possible outcomes, head and tail, and independent replication of the same experiment, then this kind of trials is known as Bernoulli's trial. On the other hand, if a simple experiment has k numbers of outcome and independent replication of this experiment, this kind of trials is known as multinomial trials. So these things are important to know the basics of these random events, which will be useful when we are going to give the concept of probability. So if we know the basics of this experiment, and based on this experiment, if we know what are the all possible outcome, then this will be helpful to understand and interpret the results of the probability analysis. And if we assign some particular probability, it will help us to infer from the results in hand. So gradually I will show in this how this kind of concept, this kind of interpretation of the probability is based on this kind of random experiment. First, one important terminology that we should understand clearly is sample space. A set, it is generally designated as a capital S, a set S that consists of all possible outcomes of a random experiment is called a sample space, and each outcome is called a sample point. Example, if a dice is tossed, one sample space or the set of all possible outcome is given by the numbers from 1 to 6. So this can be treated as a pictorial representation of the sample space, and these black dots are the sample points. So collection of all these sample points, collection of all this possible outcome for a particular experiment is known as the sample space. Second thing, just after we know what is sample space, comes as event, and a event is a subset of the sample space, or in other words, a subset of all possible outcomes. So I know what is my sample space. If I want to show it here, the black circle, the black or the red area here is your sample space, and in this sample space, if I select any combination of the sample points, then each combination or each feasible set is feasible subset of this sample points is one event. There are other terminologies like elementary event. It is very simple in the sense that if a particular sample consists of only one possible outcome, then that is known as simple event or the elementary event. If I give the example again of this throwing a dice here, so here the sample space, as I told just in the previous slide, that the sample space is any integer number starting from 1 to 6. Its event can be anything. If I say that 1, 2, 3, so this is one event. I can say that okay, the number is less than 4, so this is one event. I can say the number is exactly equal to 4, then that is also one event. So number is exactly equal to 4, that means there is only one possible outcome. And if I say the outcome is one even number, then there are three possibilities, 2, 4 and 6. Similarly, if I say the outcome is less than 5, so these are all event, and one particular event may have one or more than one possible sample points. So concept of the sample space and event is very important, that will help us to understand the concept of probabilities. Another important thing to know here is the discrete and continuous sample space.
So discrete and continuous sample space can be expressed as follows: S, which denotes the space. The S is discrete if all subsets corresponds to events. On the other hand, S is continuous if only special subsets or measurable subset corresponds to events.
Coming to the civil engineering here, so the concept of the sample space, event and the probability of that particular thing, these things should be clear first to understand the probability associated to a particular event. If I give one example, say in case of reservoir storage, the range from 0 to maximum capacity of the reservoir forms the sample space. And this is obviously, so any value can be taken from this 0 to this maximum capacity, say some maximum capacity, if I say it is capital C. So 0 to C, any value is possible, and this full range is our sample space. Now reservoir storage above the dead storage or reservoir storage below the 50% of the total capacity are the example of events. So these are, for example, the reservoir storage above the dead storage is a particular subset of the total possible sample space. So this particular thing is one event. So if I know this is the event, generally the probability are given to this particular event. So I can ask what is the probability that the reservoir storage is above dead storage, or I can ask what is the probability the storage is below the 50% of the total capacity of the reservoir. Similarly, suppose if we take the example of another random experiment, that is that traffic volume. In the transportation engineering, this is mostly used. So in case of traffic volume, if I ask that is all possible types of vehicle consist the population, the answer is no, because the traffic volume means the total number of different types of vehicle moving across a particular stretch of the road. So this is the number that I want to stress here. So that number consists of, by definition, that number is your traffic volume. So here the population, or here the total sample space for the traffic volume consists of any number between 0 to infinity and any range of these real numbers. So again here this thing is one example of the discrete sample space, because these numbers cannot be any real number. This should be an integer number. So this sample space is a discrete sample space, and any range of real numbers can be treated as an event. So I can say what is the probability of the traffic volume less than 10, or what is the probability that the traffic volume is greater than 100, this kind of thing. So any subset of this 0 to infinity, and it must be a real number, and that consists of the sample space for this experiment. Coming back to this particular thing, or before that, so I hope you understood that in this experiment, the reservoir storage, this sample space is a continuous sample space. So the first example is the example of one continuous sample space, and second one is one example of discrete sample space. Coming to again this particular question, that so for in case of this traffic volume, all possible types of vehicle is not the population of this one. Now if I ask you that what is this, means what is the collection of all possible types of vehicle, is this not can this not be an population? The answer is yes, this can also be a population. So you can ask yourself, what is the experiment involved for this if this is the population? We will come back to this particular question again, and this is very interesting, and this is very important concept at the starting of the understanding of random variable, and which we will cover maybe in the successive after some lectures. That this random variable, the concept of random variable comes that it doesn't mean that a random variable is a variable which is random. This is a completely wrong definition of this random variable, and when we discuss about this definition of random variable, we will come back to this particular question once again, and we will say that what is that particular what should be the exact definition of this random variable. Now we will try whatever we have understood so far about the sample space and its event. We will try to understand the concept of the probability here. The concept of probability was proposed to explain the uncertainty in the random events. As we told that the outcome of a random experiment is not, it cannot be ascertained. So I have to give some number, some belief, and I have to assess that particular belief, I have to assess that particular number, and this concept of probability is generally developed to give some explanation to that uncertainty in the random events. Such random events may occur sequentially or simultaneously. As we told in just previous few previous lectures, few previous slide, that any random event which is, this can be either consist of the sequentially, or this can be in a simultaneous fashion. Now in the sequentially, we will later part of this course we will also understand this sequence can be either of in the temporal direction or in the spatial direction, that is known as the spatio-temporal thing. So any particular random variable we can observe it in the time sequence or in the spatial sequence, and there are different types of analysis that we can do, and we will take you through all these things. So for the time being, we should understand that these random events can happen either sequentially or simultaneously. For example, here the simple example that I can say now is occurrence of road accident in transportation safety analysis, or occurrence of extreme, that is very high or very low rainfall, which is in case of very high, of course it is that which is beyond the capacity of the drainage network, or occurrence of the very low rainfall which may affect the agricultural production or so. So this kind of occurrence, this kind of random events is very important for our civil engineering purpose, and we will know that what are the way that we can assess the probability, and what are the way different methods of the probability can be applied to this particular to this concept of the probability can be used in that kind of analysis. In this concept of probability again, generally for a particular system, occurrence of such event approaches to a constant number. With the increase in the number of observation, this number remain constant. So for example, if I take a particular experiment in hand, and I just see for a very long record, very long historical record, and if I see that what is the chance or what is the frequency of occurring that particular event, we can say that it is generally we classify it into that success and failure, and we see that what is the chance or what is the frequency of the success of a particular thing in the historical record. And this historical record is very important here. This should be sufficiently long to assess some probability of this. Before coming to this real life civil engineering problem, I can say you one again very simple example to this example of tossing a coin again. So here the tossing a coin and observing its outcome is your experiment, and counting the outcome as head, say for a particular outcome head, or it can be tail. So this is a particular event. So if I say that tossing a coin and observing the head in this experiment, if the head comes, then it is a success, and if head doesn't come, that is a failure. So that is one event. And if I follow this approach, that is for what is the occurrence of a such particular event approach to a constant number, and by our day-to-day experiment I can say we can say that this number for this particular experiment will approach to 0.5. So this 0.5 generally we assign this particular number, generally we say this is the probability of getting head of one experiment having a coin. We'll come to this real life problem of this cyclone event or this thing a little bit later, so that it will be clear in the area of civil engineering problem also. Before that, we should know the definition, the classical definition of probability. As I told that we should have a very long record available with us, or if we are conducting the particular experiments, we should conduct the experiment for a very long time, so that the number will approach to a particular constant value. Here, based on the relative frequency, if an experiment is performed n times and an event A occurs n times, then with a high degree of certainty, all these terms are very important. So with a high degree of certainty, the relative frequency Na by n of the probability of occurrence of A, which is designated as P in bracket A, is close to Na by n. So the probability of occurrence A is the ratio of Na by n. Here you can see that this Na is nothing but the success, the number of success, and this is the total number of trial. So as I told in that this should be sufficiently long. This should be the infinite number of series of sequence should be tested to approach to that particular number. So so this definition, so if I want to know exactly what is this probability based on this relative frequency concept, then this n should be sufficiently large, and that is why we write the probability of A is equals to limit n tends to infinity Na by n. So this definition is generally based on this relative frequency concept. There are other definitions of the probability are also there. We will see it shortly. Before that, to assign the probability of a particular event, there are three different ways that we can assign a particular probability for a particular event. Say for example, here the event is AI. To assign the probability PA of a certain event in an inexact way. Suppose this way of assigning the probability, I have to see the historical record of a particular experiment, and based on the historical properties, based on the historical success rate of that particular experiment, I have to assess some number. So as this historical record is never never an infinite series, that's why we say it as the inexact way. Here one example is that if out of 365 days in a year, there are 73 days are recorded to be above average rainfall, then we say the probability of event above average daily rainfall is 73 by 365. So this 73 for this experiment is the success, and the total number of trial, total number of days, total number of experiment is your 365. So this is an inexact way of assigning the probability to a particular event A. The second way, that is to make an analytical reasoning for the event which is for which probability is to be assigned. So this analytical reasoning again is one of the most important thing to understand with respect to the different already established concept. That is, I generally follow some norms and to develop some particular material in civil engineering, or say I have some particular belief in me. So in this way, if I know that the way the definition is given for a particular particular attribute, I should say, and if I know what was the background to give that particular event, then I can assess that probability given related to that particular event. Here one example is given here, that if you already know the basics of the civil engineering, then I hope you know the M20 grade of concrete. If you don't know, this is a particular grade. There are different grades of the concretes are available, say M15, M20, M25, M25, M30, 35, 40. It can have, so different grades of the concrete is there. By definition of this particular grade of concrete, it says that this is a characteristic strength, and it is defined as if a concrete cube, and that concrete cube dimension is 15 centimeter by 15 centimeter by 15 centimeter, and if we say that this is made of M20 grade of concrete, and this cube is subject to a pressure of 20 megapascal Newton per millimeter square, then the probability of the event that a cube will fail is 0.05. Now where from we get this 0.05 is lying in the definition of the characteristic strength. So this characteristic strength, the definition of characteristic strength says that what is the this means what is the strength at which I can assure that at least the failure that failure of that particular concrete cube will not exceed 5%. So that is why, so if I take a M20 grade concrete and the pressure is 20 MPa, so that the probability that the event the cube will fail is 0.05. So this is one analytical reasoning, an example of this analytical reasoning of assigning probability to this particular event. And the third one is that a kind of deductive approach. Assume that the probability follows certain axioms. We will come to this one, the axioms of probability, and then by deductive approach determine the probability of an event using the probability of other events. So there are different kinds of events is available, and somehow say you assume for the time being that somehow I know the probability of a particular event. Now using this information that I know the probability of this particular event is this, then if the question comes that what is the probability of some other particular event, then I should be able to assess, I should be able to compute the probability of this particular event using the information of the probability of the available information of the probability of some other event. So this is a deductive approach. Suppose that here, because this will be more clear when we cover this this axioms of probability, but before I cover this one, this is a very easy example that must be you should be able to understand, is the probability that a testing device, there are different type of testing device available in civil engineering. Suppose that testing device is a company has given it to the market, and based on the customer satisfaction, the customer will categorize that particular testing device as very poor, average, satisfactory, and excellent. So based on somehow from the market study or some other way, the company knows that a particular testing device to be categorized as very poor, the probability of this to be categorized as very poor is 0.05, to be categorized as poor is 0.15, average 0.68, satisfactory 0.1, and excellent 0.02. Then if the question is the what is the probability that the same device will be rated as above average. So if I say it is above average, that means it should be either satisfactory or excellent. Now there are obviously some assumption background to this, that a particular customer cannot categorize is at both satisfactory and excellent. If he categorizes as satisfactory, so he is having only one choice. So these two, particularly these two events of categorizing as satisfactory or excellent is mutually exclusive. Again, the definition of mutually exclusive says that the occurrence of a particular event ensures that non-occurrence of the other event. So for example, the tossing of a coin, if I say that outcome is head, then it is automatically implies that the tail has not occurred. So in other words, the head and tail, both the outcome cannot happen simultaneously. This kind of events are known as mutually exclusive. Okay, and if I say that these two things are independent, so if one customer has categorized as satisfactory and another one has categorized as excellent, and this categorization by different customer is independent to each other, then I can, if I want to know what is the probability that the particular device is rated as above average, this will be simple summation of the probability available for this satisfactory, this above average, satisfactory, and excellent, that is 0.1 plus 0.2. So here in this way of assigning the probability of a particular event, here the event is above average, means this rated as above average, this is particular event is based on, not based on any particular experiment, this is rather based on the information that is available on the probability of some other event. So this is the thing, this is a deductive approach, that's why this is deductive approach, and it is determined by the probabilities of the other event for which the probability is known. So these are the three different ways that we can assign probability to a particular event. So just in the previous slide we discussed about the axioms of probability. So different type of concept of this probability can also have the different way. Just now we have seen that what is the relative frequency, the concept based on the relative frequency. There are other concepts also. For example, here the axiomatic definition. So there are few axioms that is there for a particular probability event. There are basically three axioms are there. For probability of PA is a non-negative number. So this PA is always greater than equal to 0. This is the first axiom. Second is the probability of all events in the set is unity. So the probability of all possible outcome of a particular event is equals to 1. And the third one is the probability of event A union B is the addition of the probability of A and probability of B. That is, probability A union B equals to probability A plus probability B. Here this symbol, that is A union B, is the union of two events A and B, is defined as an outcome when A or B or both has occurred simultaneously. In the concept of the Venn diagram, you know that if this is your probability A and if this is your probability B, so the first circle what I am showing as a black dotted, if this is your A, and if the red dot that have given, if the red shaded area, if this is your B, then A union B is the summation of the both. So this total area is your A union B. So this is the two different events, and so if they are union, so the probability of this total event is nothing but probability of A plus B. But there is a condition here that these two events are mutually exclusive. Why? Because here if you again see this one, that if I say that this area is your probability A and this area is your probability B, then if I just simply add this one, then this area obviously which is common in A and B will be added twice. That's why when it is mutually exclusive, then I can say, suppose that this is your A and this is your B, then probability A union B is nothing but probability of A plus probability of B. Now based on these three axioms that we have discussed, we can reduce different numbers of equations where we can use it for the deduction of the probability of the others. For example, in case of this when two events are overlapping each other, then what should be the probability of A union B? That you can easily say that probability of A plus probability of B. In this process we have taken this area twice, so this should be minus, this area should be given as a minus, and that is probability of A another new way of this is the intersection of B. So probability, this symbol, this probability A intersection B is nothing but this particular area where it says that this is the common in both the events. So as we have in this process we have added this area twice, so this should be deducted here. So this second one is your these are the three axiomatic definition where we can following the deductive approach we can get the probability of the other events if the probability of the particular events of some other events is known to us. The third one is the classical definition. The classical definition, the probability of an event A, probability A is determined without the actual random experiment as a ratio as follows: probability A equals to probability NA by N, where NA is the favorable outcome related to the event, there will be one T, to the event A, and N is the total possible outcome. That means we are not exactly following any particular random experiment. Whatever the observation is available to us, based on this, whatever the ratio of this success out of the total number of trial, we are assigning this particular number, which is the classical definition of this probability. It is implicitly assumed in this event that all possible outcomes of a particular experiments are equally likely. Coming to the throwing of a dice example, that all possible outcome, that is any integer number from 1 to 6, the outcome should be, all these outcomes should be equally likely. So the probability of getting 1 should be equals to probability of getting 2 equals to all these numbers should be equals to 1 by 6. So from our day-to-day experience, we generally assign this probability, and this, when we say that yes, all these probabilities are equal and equal to 1 by 6, then all these events are equally likely. Basically, this is a point where this basic concept of probability is questioned, and sometimes this kind of critical views are thrown to this basic concept of this probability. The term equally likely actually means that equally probable or fair choice, which is not always feasible in the practical cases. It is not possible for the practical cases. We basically having a fair dice or fair coin is impossible, even though you go for a very large number of trials, and how large is large to get that particular probability of a head, say 0.5, or for a dice for a particular number is 1 by 6, is that whether they are really equally likely, that cannot be ensured always. So this is the first thing that generally face the problem of this classical definition. Second thing is that the definition is applicable to the limited practical problems, since the equally probability of the choice is hard to achieve. So even though there are some experiments that by choice or by the experience we say that all these possible outcomes are equally likely. So for those kind of experiments, this definition can be applied. But whatever, there are many other examples where this kind of equally likely events cannot be assured. So in such cases, the applicability of this classical definition generally throws the question here. And the third thing is that the number of possible outcome is infinity. Now, if for a particular experiment, if I say the number of possible outcome is infinity, then some kind of measure to the infinity should be assigned to get the ratio of the n. Say for example, if the example is given like this, that in a circle is there, and there is another circle inside this, and one random event is that there is a chord here. What is the probability that this chord, some part of this chord, will be inside this inner circle as well? So there are two chords I can just draw now. One is that this is passing completely outside this inner circle, and another one is passing inside this one. Now if I want to assess the probability of this kind of experiment, then some kind of what is the total possible outcome should be there. So means experimentally I can draw any line here and say that there are this many chords are possible. So I have to some kind of assessment of this area. Okay, this area, if it goes, this is outside, and if it goes in this area, this is outside. So this can be achieved in different ways. The first thing is that if I know the origin of these two circle, one way is that we can just start for any point and say that this is one, and there is another chord like this, and I should say that this is the angle which is my favorable case. So all chords in this area will pass through this circle, and all others are this one, so that this area divided by the total area can give the probability. Second way of looking the same problem is that there is one outer circle and there is another inner circle as well here, and I can draw two particular chord here like this, and say that all possible chords that is in this area are my favorable case, and all other except all other which are falling outside, that is the non-favorable case. So this area divided by total area will give this the probability. There is a classical example is known that these two probabilities sometimes may not match to each other. So this is also one particular drawback of this classical theory. And when we are going to give that favorable and non-favorable to non-favorable ratio, when we are computing the ratio of this favorable case and non-favorable case, so the definition of this, how this experiment is performed, whether with respect to the experiment this particular thing is more feasible or this one is more feasible, is to be justified first, and then the probability should be calculated. And this is particularly in case of when the possible outcome is infinite. That kind of problem may arise. So validity of the classification definition in application, the assumption of having equally likely outcomes can be established through a long experiment, through a long experiment size. Say for example, that if I take an example of occurrence of cyclonic storm is random in the time interval of 0 to t, then the probability that it may occur in the interval t1 to t2 is equals to t2 by t2 minus t1 divided by t. So 0 to t some time interval I am taking, and I am saying that the occurrence of this cyclonic storm is random, and I am implicitly assuming that this occurrence is equally likely over any time in this time interval. Then what is the probability that it will, obviously this t1 is greater than 0 and t2 is less than t. Then in this area, of course, that means this t1 and t2 are lying in the range of 0 to t. Then the probability of this cyclonic storm occurring in this time interval is equals to, basically this is t2 minus t1 divided by total possible t, capital T minus 0. So this is the so in this kind of analysis, when we are assigning this probability, we are implicitly assuming that the outcomes are equally likely. If it is impossible to repeat an experiment sufficiently large number of times, assumption is made that the available alternatives are equally likely. This is basically the start point of the probability theory. When this kind of experiments cannot be run in a large number, this is implicitly assumed that all possible outcomes are equally likely. Now the determination of probability, the assigning the probabilities pi of a certain event in an inexact way. Second, this is, we have discussed just whatever the available record that is available with us, and in that what is the number of success and what is the total number that is available. That ratio gives you that probability for that particular event. Second, theory of probability follows certain axiom. So just now we have seen what are the axioms that a probability follows. So probability of a particular event can be determined by the deductive approach. And third one, what we have seen, that make a physical guess of the event based on the probability numbers calculated pi and jb. This probability and occurrence, I think this is needed at the starting of this course to know that what is this probability and what is the actual occurrence in the real field. Suppose that I say a particular experiment, say that the rainfall event, event occurs more than what is the capacity of my drainage network. So this is a particular event, that rainfall amount greater than the threshold value which should be our drainage system can take care. And I say that this probability is say 0.05. So now the thing is that if I say that this probability is 0.05, now the question is that in the next event of the rainfall, what is the chance, what is the occurrence that that particular rainfall value will really exceed. So what does this 0.05, what does this number actually give you to infer? This is the topic of this particular slide. So if the PA is known, the PA means that probability of a particular event is known, the occurrence to the question is if it is occurrence to the next trial can be based on the size PA. So now this size of PA matters the thing here. The first thing that if the PA is low, say for example 0.3 it is given, then it concludes that only a certain degree of confidence the event A will occur. It doesn't mean that exactly you perform 10 trials and exactly 3 trials will be your success. That is not the case. So in a long term, so that is with certain degree of confidence. So this is very important, the certain degree of confidence, that is the thing that you can infer from here. So it is a measure of belief that, and this thing generally cannot be experimentally tested. So this is a subjective thing of the measure of this belief that with this degree of certain confidence that this particular event A will occur. Second thing is that if the probability is very close to 1, that means say for example 0.999, it concludes that with the practical certainty A will occur in the next trial. So if very high probability, then we generally say that with the practical certainty this will definitely occur when the probability is very high. So the probability when it is very low, it is very unlikely to occur, and when it is very high, generally we say that it is likely to occur. But it never say that exactly if you consider some n numbers of trial and it will happen exactly the probability number multiplied by this total number of trial, it may not occur in that exact number way. So the probability and occurrence of a particular event should be understood in it should be assessed in this particular way. And the last thing, but this is also important, the randomness and causation. So this randomness links with the probabilistic system and the causation links with the deterministic system. The randomness is stated with certain errors and certain range of these relevant parameters, and causation is stated with a high degree of certainty if the number of the outcomes is large enough. But again, basically there is no conflict between the randomness and causation, because when we say that there are some laws of this nature, this theory, since the theories are not the laws of nature, both statements are true. So even though I say that a particular system is deterministic, that deterministic system we just for our simplicity's sake we have just said that this is a deterministic system. But if we really see that whether that particular system is exactly deterministic or not, there is a little bit of randomness maybe there as well. So basically that's why it says that basically the conflict between the randomness and causation are not there. These are just basically some concept, and if it is clear, then it is generally very useful to the thing. The final concluding remarks is this, that in this lecture we have seen that random events are possible outcome of the random experiment, and probability is a measure of the uncertainty in the occurrence of them. Random events consist of either single point or multiple points of the same sample space. The relationship among the random events are governed by the set theory and the event properties, and this set theory and these event properties will be explained in the next lecture of this course. Thank you very much.